Good day to everyone. So in this video, we are going to discuss about the finite difference method to solve the partial differential equations. So in order to implement the finite difference method to solve the partial differential equation, so you are going to consider two different equations. One is the Laplace equation, and another one is the Poisson equation. Poisson's equation. So we are going to consider these two equations. That means the Laplace equation, you already know this, u of xx plus u of yy, which is equal to 0, and the Poisson equation which is given as u of xx plus uyy, which is equal to some g of x comma y. Okay, so we have taken this Laplace and the Poisson equations with the boundary values. That is, the boundary conditions to solve the Laplace equation is the u of x comma y, which is equal to the function of x comma y. So this is the boundary condition for the Laplace equation, and for this the Poisson equation, we have a u of x comma y, which is equal to some g of x comma y. So these are the boundary conditions, and these boundary conditions are actually known as the Dirichlet boundary conditions, and the problem which we are going to consider is also known as the Dirichlet boundary value problem. So in order to solve this equation, we are using the finite difference method. We already know what is finite difference method. That means how this finite difference method is actually works when you are solving the partial differential equation. We have seen this finite difference method for the ordinary differential equation with the boundary value problem. The same idea is actually implemented into the partial differential equations also. That is, in ordinary differential equation, we have differentiated. We have find the solution in the as a function of x. However, in the partial differential equation, the solution of u is actually depending upon the both independent variables x and y. So that what we have to do is we have to implement this finite difference method both x and y direction. Okay. Suppose if you have a two-dimensional domain like x comma y, which is having the dimension of r, and we are going to superimpose this domain r into a mesh network, a mesh of lines. That means the value of x is varying in the x direction and y is actually varying in the y direction with the time step of each time step of, let us take the x is actually varying with the time step of h and y is actually varying with respect to the time step of k. Sometimes if the h is equal to k, then you get the square like mesh point, mesh structure. Otherwise, if k is not equal to k, then you will get the rectangle like structure. So this mesh lines are actually known as the grid points, and the points of intersection of this mesh lines is also called the nodes. Suppose if this 2 points actually intersect, that means that the x-axis and y-axis actually intersecting at this point. So these points actually called as the mesh points or a grid points or nodal points. So at each and every point, they will actually having the values of x and y, x1 and y, all the values x and y with the time step of h and as well as k. So the mesh lines of the x-axis and y-axis actually can be defined as xi, which is equal to xi times of h. Similarly, the yj, which is equal to j times of h, where this I is actually running from 0 to n, and this j is actually also running from the value of 0 to n, m, maybe n is equal to m or n is not equal to m. And we are going to find out the solution at these points, at these nodal points. We are going to find out the solution of the partial differential equation, because as a function of x as well as y, the u is actually varying. Suppose if you solving this partial differential equation analytically, then you get the solution in all the space. That means the entire space of the equation. However, if you use the numerical integration, then you already know that you have to discretize the discretize the space with some time steps h as well as k, so that you can find the solution at this point. So if you want to find this point, then you need this points, right? So these points are actually known as the boundary points or boundary values. So these boundary values is already given, provided with the equation itself, so that using this point you can find the next point using the equation which we are using to solve to use the finite difference method. So the true solution of this equation is actually in terms of writing it in terms of x and y. And if you are integrating this equation, I mean, you are discretizing this equation in the numerical for the numerical integration, so that the corresponding numerical solution can be written as xi comma yj, that can be written as u of I comma j. Okay. So this the solution of x and y is actually discretized in terms of I runs from 1 to I and j, and which can be written as u times u of ij is the numerical solution which we have obtained from this equation or from this method. So when you start integrating the corresponding equation at this nodal points, the partial derivatives of the differential equations are replaced by the suitable difference approximations. That means you are actually converting the differential equation into difference equation. That is the partial differential equation is approximated by a difference equation at each nodal point of this mesh point. So this procedure is also, we already know this is a discretization of the partial differential equation. So once if you want to do this, then you can use the finite difference method. So the finite difference method equation, we already know that. Suppose if you are actually using the central difference approximation method to solve the first order approximation, then the ux of the I comma j is actually varying in the terms of 1 divided by 2 times of h, and u of I plus 1 comma u of I plus 1 comma j minus u of I minus 1 comma j. So when you are applying the finite difference method for the ordinary differential equations, you don't have the two different incremental points. Only you have the one variable which is actually varying with respect to the I, so that you get the I plus 1 minus I minus 1. But here you have two different the x and y axis are varying, so that you have the two different incremental operators, means the incremental variables I and j. So once if you are considering the x is actually varying, then the I is actually the incremental variable for the x, so that you will get the I plus 1 and I minus 1 is this is the equation for this u of ux of I comma j. Similarly, I can write this same equation for the y term also. So u of y I comma j, which is equal to 1 divided by 2 times of k u of I comma j plus 1 minus u of I comma j minus 1, because this y is actually incremented in terms of, the j is actually the incremental variable for this y, so that the I plus j and I minus j is actually varying for this uy, to finding the uy. And also you can see that this one the incremental time step is actually k, so I have used 2k. So these are for the first order derivative. Suppose if you are again using the second order derivative, you can also go for the central difference approximation. For example, uxx of I comma j can be written as 1 divided by h squared u of I plus 1 comma j minus 2 times of u I comma j plus u of I minus 1 comma j. So this is the second derivative approximation for the x variable. Similarly, u of y of I comma j can be written as 1 divided by k squared u of I comma j plus 1 minus 2 times of u of I comma j plus u of I comma j minus 1. So these are the first and second order derivatives. Now you can directly substitute these values into the Laplace equation to find the final equation, the final value, final relation. So the solution for solution of Laplace equation So the Laplace equation is u of x plus u y, which is equal to 0. So I just convert this the differential equation into difference equation, that is u of x I comma j plus u y of I comma j. Now we know this values of this uxx and uyy from this second derivative of the central difference approximation. I can just substitute these values here. So that what we get is 1 divided by h squared u of I plus 1 comma j minus 2 times of u of I comma j plus u of I minus 1 comma j plus 1 divided by k squared u of I comma j plus 1 minus 2 times of u I comma j plus u of I comma j minus 1. I just substituted these values, so which is actually going to be equal to 0. So in order to simplify this equation, what I am going to do is I am going to multiply the right hand, this left hand side with the h squared, so that multiplied by h squared this equation. So this h squared will get cancelled. You will get the h squared divided by k squared. So the h divided by k, I can take it as another variable p, because this h and k are constant values for the particular equation. So I can take it as a p, so that I can rearrange this equation as u of I plus 1 comma j minus 2 u of I comma j plus u of I minus 1 comma j plus p squared of u of I comma j plus 1 minus 2 of u I comma j plus u I comma j minus 1, which is equal to 0. And if suppose we have taken the h is equal to k, that means you have considered the square mesh points, that means a uniform mesh spacing point, then h is equal to k, that means the p will be equal to 1. So that if you substitute this value, we just consider the assumption h is equal to k, then you can take this equation as when they just collecting the variables of the coefficients of I plus 1 and I. Now we can finally write the final form of this equation as u of I plus 1 comma j plus u of I minus 1 comma j plus u of I comma j plus 1 plus u of I comma j minus 1 minus 4 times of u of I comma j, which is equal to 0. So this is the approximated is the equation of the Laplace equation. So where this equation, this approximation also called as the standard 5-point formula, because you have the 5 different nodal points in this equation. So that this equation is called as the standard 5-point formula. So if you want to find out the u of I comma jth point of the corresponding equation, then from this equation I can write it as u of I comma j is equal to 1 divided by 4 times of u of I plus 1 comma j plus u of I minus 1 comma j plus u of I comma j plus 1 plus u of I comma j minus 1. Okay. So now you can see that once if you want to find out this u of I plus I comma j, you need the nodal points at this four different values, I plus 1, I minus 1, as well as j plus 1, j minus 1. Okay. So suppose if you go back to this mesh point, suppose if you consider this is the u of I comma j, then this is the I plus 1 point and this is the I minus 1. Similarly, this is the j plus 1 comma I comma j plus 1, and this point is actually known as the I comma j minus 1. So if you want to find out this point, then you require the values of these 4 points. Sorry, this is the I minus 1 point, I minus 1 comma j point. So if you want to find out this point, solution of this point, you require the values of these 4 points. And if you know these values, then you can use this, using this formula, you can find out the solution of this point. Okay. So once if you know this point, then you can find the next, you can just spread this solution to the everywhere, to all the mesh points. So this nodes actually numbered in the ordered way. Suppose if you want to number the nodes in that this is the node point. So U1, U2, U3 are the solutions. Suppose if you want to name number these nodes, this one, so all these intersected points of x and y, then you have to use some order. That means if you are actually number them from the left to right and from the top to bottom or from bottom to top. Okay. For example, if you start this numbering this mesh points is this is u1 and this is the u2, u3, and then you have to go to the bottom side, then you can increase the values. Okay. Otherwise, you can start from this left hand side, the bottom side, then you can increment from here, and then you can go to the bottom to top of a procedure, or from the top to bottom procedure. Okay. So in order to find the system of equations for the Laplace equation, and we are going to number these values. You can choose this mesh point as this. Then I am going to number this point. Find out the solution of this point u1, u2, u3, and write this equation. Write this point as a system of equations. So suppose if you consider the at the first point, that means you are going to find out the solution of this u1 using this 5-point approximation formula. At this point of u1, u2, u3, and so on. So up to the ninth point, I am going to find out what is this values of u1 based on this 5-point approximation formula. So I am going to write it for 1. That means at 1. That means u1. So you're going to find out that you have the values of u2, u4, and this is not known. That these 2 points are not known. So only the two points are actually known to find out the values of u1, so that I can just substituting this u of I plus 1 comma j, and u of I minus j comma j minus 1 comma j minus 1 I comma j minus 1 using this formula. Okay. So I'm going to write this at this point u1 point. I have the solution as u2 plus u4 minus 4 times of u1, which is equal to, we have some boundary values, right? So this values and this values are not known, so that I can take it as a b1. That means the boundary value b1, or I can write this equation as this increment of u1, u2, u3, so that I can write it as minus 4 times of u1 plus u plus u2 plus u4, which is equal to b1. Okay. Similarly, I can find the value at 2. That means at this point, now we have the I plus 1, I minus 1, and j minus 1, but we don't know what is j plus 1 is. So that I can write this equation as, so u1 plus u5 plus u3 minus 4 times of u2, which is equal to the boundary value 2. So similarly, I can write this in the order values, so that u1 minus 4 times of u2 plus u3 plus u5, which is equal to b2. Okay. Similarly, I can calculate this point at 3. At 3, we don't have what is I minus I plus 1 is, but we know what is I minus 1. Similarly, j minus 1, we know that. So I can just substitute the values of the corresponding values. u2 plus u6 minus 4 times of u3, this is equal to the boundary value 3, because we have the boundaries here. So similarly, I can just writing this into incremental values. So u2 minus 4 times of u3 plus u6, this is equal to b3. And for at 4, that means at this point 4, we have the 3 points. That means u5, I plus 1 we have, I j plus 1, j minus 1 we have, but we don't know what is I minus 1 is. So that I can write it as u1 plus u7 plus u5 minus 4 times of u4, which is equal to the boundary value 4. And I can write this as u1 plus, minus 4u4 plus u5 plus u7, which is equal to the boundary value 4. And at 5, so in 5th point, you can see that you have all the points, right? So you have all the boundaries, plus 1, I plus 1, I minus 1, j plus 1, j minus 1. So that I can write there at first point u2 plus u4 plus u8 plus u2 minus 4 times of u5, this is equal to 0, because we already have all the boundaries. So the boundaries, the remaining boundary is 0. So that I can write this again. I can just rearrange this equation as u2 plus u4. Sorry, this is actually u6. So u2 u4 plus minus 4 times of u5 plus u6 plus u8, which is equal to 0. And in the same way, I can write the 6, 7, 8, 9 also. Okay. So I can just quickly writing it at 6 we have the u3 plus u5 plus u9 minus 4 times of u6, which is equal to boundary 6, which can be written as u3 plus u5 minus 4 times of u6 plus u9, which is equal to the boundary 6th boundary. At 7 we have u4 plus u8 minus 4 times of u7, which is equal to boundary 7, or I can write this as u4 minus 4 times of u7 plus u8, which is equal to boundary 7. At 8 we have the u5 plus u7 plus u9 minus u4 times of u8, which is equal to the boundary 8, or u5 plus u7 minus 4 times of u8 plus u9, which is equal to boundary 8. And finally at 9 we have u6 plus u8 minus 4 u9, which is equal to the boundary 9. So I can write it as u6 plus u8 minus 4 times of u9, which is equal to the boundary 9. So now we have the linear algebraic system of equations. So if you solve this equation, then you can easily find the solution of the corresponding u and corresponding I comma j values. So you can write this set of equations into the matrix form, which will give you this kind of matrix. So this matrix is actually known as the structure of this matrix is actually known as the band matrix. So that this matrix can be taken as A, and the solution of this u1 can be taken as u, then which is equal to d. That means that the boundary. So this is the corresponding form of this the system of algebraic equations. So once if you solve this matrix using the Gauss elimination method, or you can just solve the set of equations, then you can find out the unknown values of whatever the values of u1, u2 from u1 to u9. So this is the finite difference method for the Laplace equation. Now we are going to see one of the examples to solve the Laplace equation using this finite difference method. Okay. So the first example problem is you have to solve the Laplace equation ux plus uy equal to 0 numerically for the following mesh with uniform spacing and with the boundary conditions as shown in this figure. So this is the mesh values they have given. So the mesh is actually given as A, B, C, D, and you have to find out what is the values of u1, u2, u3, and u4. Now the boundary conditions are given here. So you can see this boundary condition 3, 6, and everything is given here. And when you look into this mesh points, you can find that this partial differential equation and the boundary conditions are also already symmetric about the diagonals of AC and BD, isn't it? Suppose if you draw a diagonal line here, so you can see this. There is a symmetric way of boundary conditions 6 and 6, 3, 3. Similarly, you can see the 3 and 3, 6 and 6 here, or you can just plot a diagonal line here. You can see that the symmetry is actually still maintained, isn't it? So that what you can do this, we know from this mesh point we know this u2 is u1 is actually equal to u4. Similarly, the u2 is actually equal to u3. So to find a find solution. So the u1 which is equal to u4 and u2 which is equal to u3. So once if you find out the solutions of the u1 and u2, then automatically this corresponding values are equal to the u4 and u3, isn't it? So that we don't require to calculate the values of all the u1, u2, u3 as well as u4. Only just finding out the values of u1 and u2, then remaining will be automatically just we can use the same values for the corresponding the other u values. So in order to solve this equation, we are again going to use the standard 5-point formula. So u of I plus 1 comma j plus u of I minus 1 comma j plus u of I comma j plus 1 plus u of I comma j minus 1 minus 4 times of u of I comma j, which is equal to 0. Okay, so since this is the Laplace equation, we are going to use this equation. So at point 1, that means 1 means at u1 If you want to find out this values, you need the 4 different values, right? This one, this one, this one, and this one. I already have this value, so that I can write this equation. I mean, I can write this using this values. I can write this equation as u2 plus 3 plus 3 plus u3 minus 4 times of u1, which is equal to 0. Or I can write this equation as minus 2 times of u1 plus u2, this is equal to minus 3. So I can just simply add this 6 and just dividing this, substituting the values of u2 is equal to u3 in this equation. You get the 2u2 and minus 4u1 into plus 6, so that you can just divide all these values by the 2. You will get this final equation. And similarly, at the point 2, at 2, that means at u2, you can find the values of 6 plus 6, that is the boundary values, plus u1 plus u4 minus 4 times of u2, which is equal to 0. So again, I can write this equation just substituting the values of u4 and u2 or u2, then I can find the values. The final value is 2 u1 minus 4 times of u2, which is equal to minus 12. So now we have the two set of equations, a set of different algebraic equations. Suppose if you add these two values to two equations, then these two u1 value get cancelled, so that the value of minus 3 u2, which is equal to minus 15, or u2, which is equal to 5. So I have calculated the values of u2. Then you can substitute the values of u2 in any one of this equation. Then 2 u1 is equal to u2 plus 3, which is equal to 8, or u1, which is equal to 4. So the values of u1 and u2 is already found. Then you can just substitute the same values into the u3 and u4. Okay, so the values of u1, which is equal to 4, u2, which is equal to 5, and u3, which is equal to ultimately u2 equal to u3, so that u3 is also having the values of 5 and u4, which is having the values of 4. So if you substitute all these values here, so this is 4, this is 5, and this is 5, and this is 4. Okay, now you can again look into the symmetry property, then it's actually perfectly symmetric. Now you can find this solution of this points u1, u2, u3, 4 in the using this mesh and boundary values. So similarly, I will explain one more example. So the next problem is to solve the Laplace equation numerically for the following mesh with uniform spacing and with boundary conditions as shown in this figure. So the boundary values are given in this equation. You have to find out the values of u1, u2, u3, and u4 using the boundary values given. So you can see this problem. This is not actually symmetric with both the diagonal values, but only with the diagonal values with the diagonal of the d and b. So that if you find out the values of u1, then you can find out the values of u4. So and you have to find out the values of u1, u2, and u3. That means you can get the set of 3 algebraic equations, and you can solve them using the Gauss elimination method. So from this mesh point, you can write as u2, which is equal to u3, and u1, u2, u3 values you have to calculate. Okay, again I am going to use the same 5-point formula. The u of I plus 1 comma j plus u of I minus 1 comma j plus u of I comma j plus 1 plus u of I comma j minus 1 minus 4 times of u of I comma j, which is equal to 0, and I am going to find out the at 1. That means at u is equal to 1, we have the points of the point values are given here. So from this, just substituting these points in this equation, I can get u2 plus 2 plus 2 plus u3 minus 4 times of u1, which is equal to 0. Or I can just rearrange this equation as minus 2 u1 plus u2, which is equal to minus 2. Just substituting the values of u2 equal to u3 here, so that I can get the final equation here, this one. Similarly, I can find the values are equal to the second point, 6 plus 4 plus u1 plus u4 minus 4 times of u2, which is equal to 0. Or I can just rearrange this, just substituting the values of again the rearrange the equation as u1 minus 4 times of u2 plus u4 which is equal to minus 10. Similarly, at fourth point, because we already know this third point, 8 plus u2 plus u3 plus 8 minus 4 times of u4 which is equal to 0, and I can just rearrange this equation as 2 times of u2 minus 2u4 which is equal to minus 8. Now we have the set of three algebraic equations. Either you can solve it directly from this just doing the algebraic method, or you can use the Gauss elimination method. So in order to use this Gauss elimination method, I can just collect the coefficients of u1, u2, u3 and u4, and I can write it as in terms of matrix form, which can be written as minus 2, 1, 0, and this is 1 minus 4, 1, 0, 1, minus 2, and the values of the right hand side is minus 2, minus 10 and minus 8. So if you want to use the Gauss elimination method, you have to make this this first element as 1, so that in order to do that, I can do the transformation r1 divided by minus 2, so that if you do this for the row 1, I can get the values. I can get the matrix as 1 minus 1 by 2, minus 1 by 2, and this is 0, 1 minus 4, 1, 0, 1 minus 2, and this value is minus 1, so this will be also 1, and this is minus 10, and this is minus 8. Now we want to make this the first element of the second row is actually make it as a 0. So in order to do that, I can just divide this, subtract this the two rows. So R2 is equal to R2 minus R1. If you do this, then 1 minus 1 by 2 is 0, and this is going to be 0, and this is minus 7 by 2, and this is 1, 0, 1 and minus 2, and this the right hand side value is 1, minus 11, minus 8. So in order to make this the second element of the second row as 1, I am going to do the another transformation, R2 divided by minus 7 divided by 2. If I do this for the row 2, the whole entire row 2, I can get the values as 1 minus half, 0, here this is 0, this is 1, this is minus 2 divided by 7, and similarly 0, 1 and minus 2, and the values of the 1, minus 11 divided by 2, that's this is around 22 divided by 2, because we have the 2 in the inside, in the denominator, and this one will be the minus 8. Okay. So again, this third element is also going the second element of the third row is also, I want to make it as a 0. So in order to do that, what I'm going to do is the transformation as R3, which is equal to R3 minus R2. If you do this transformation, 1 minus half, 0, this is 0, 1 minus 2 divided by 7, and here you'll get the 0, 0 and minus 12 divided by 7. 1, 22 divided by 7, so this is not the minus here, you will get only 22. 22 divided by 7 and minus 78 divided by 7. So now this matrix is almost simplified, and if you just multiply these values, and you can find out the values of the last equation, u4 which is equal to 78 divided by 12, which is equal to 6.5. So u4 is the value of u4 is 6.5, and substituting this u4 into the second equation, you get u2 which is equal to 22 divided by 7 plus 13 divided by 7, which is equal to 5. Okay, so the value of u2 is 5. Now substituting this into the 5, so first equation you will get u1 is equal to 1 plus 5 divided by 2, which is equal to 3.5. So now we have found the values of u1, u2 and u4. The value of 5 is also equal to the value of u3 now, so that you can find the values of all the mesh points u1, u2, u3 and u4 for the given problem. So in this similar way, you can solve all the Laplace equations using this 5-point formula. Okay. So we hope you understand the how to use the finite difference method to solve the Laplace equations with this example. And in the next class, we are going to solve the Poisson's equation using the same finite difference method, and how to solve the finite difference method. I mean, solve the using the finite difference method. How using the finite difference method, how to solve the Poisson's equation. We can see in the next class. Okay, thank you.